Hi folks, a particle represented by this yellow dot is free to move on a horizontal straight line. We are going to take the rightward direction as positive and the leftward direction as negative. So a positive velocity means the particle is moving to the right, and when it's moving to the left, the velocity is negative. The velocity versus time graph is given. As you can see, it's a curve. At time t equal to 0, it starts at v equal to 0. That means it starts at rest. And its velocity keeps increasing and stays positive. That means the particle is moving to the right and it's moving faster, faster, faster. But this is not a straight line graph. A straight line graph would represent a constant acceleration. So this is an example of a non-constant acceleration motion. Now two instants of time are chosen, Ti and Tf, T initial and T final, and we wish to find the displacement of the particle for this time interval. How do we go about doing that? Supposing the velocity was constant, as in this example, it's constant with a value of v1 during a time interval delta t. So now we know the displacement, we can write it down immediately, that is v1 times delta t. Now check this out, v1 is the height of this rectangle consisting of the yellow line, which is our velocity versus time graph, the two vertical lines indicating the endpoints of our time interval, and the t-axis. Now the area of this rectangle is nothing but height v1 times delta t. So this is equal to the area under the graph, that area. Now area under the graph, what does that mean? In physics and in mathematics, area under the graph means the area bounded by our graph, v versus t graph, the horizontal time axis, and the vertical lines representing the initial and the final times. Let's see what happens if at the end of delta t, the velocity changes to v2, a different value, which remains constant for another delta t, after which it changes to another value v3. Let's see what the graph looks like. The graph looks like this. So in this example, we have three intervals of time, delta t followed by another delta t followed by another delta t, during each of which the velocity is constant but at different values. For the first delta t, the velocity is constant at v1, so the displacement is v1 delta t, which is, as we saw, the area of this rectangle. Plus, for the second delta t, the displacement is v2 delta t, which is the area of this rectangle. And for the last time interval delta t, the displacement is v3 delta t, but note that v3 is negative, but areas are usually positive. So what do? So we are going to adopt a convention that areas measured below the time axis are to be counted as negative. See, the area of this rectangle is this height, which is the magnitude of v3 times delta t. v3 delta t is a negative displacement, so we are going to take this area, which is the magnitude of v3 multiplied by delta t, and we are going to take the negative of that to get v3 delta t. So now what we have is a step graph consisting of steps, and the area under the step graph, this plus this minus this, is going to be our total displacement. So when we say area under a graph, now it means the area enclosed by the actual velocity versus time step graph, the time axis, and the vertical lines representing initial and final times, with the added proviso that areas below the time axis are to be counted as negative. So now we know how to find the displacement for a step graph. A step graph is one where we have intervals of time during which the velocity remains constant, sometimes positive and sometimes negative. What do? All we have to do is take this area plus this area plus this area minus this area and minus this area. That will give us the total displacement of the particle from this instant of time to this instant of time. But what about a velocity versus time graph, which is a curve, like the one we started with? What shall we do with this one? We know what to do to find the displacement of a step graph, but we don't know what to do with a curve. So what we are going to do is approximate this curve using a step graph like so. The white step graph is an approximation to our curve. Let me show you how I got this step graph. We start by dividing the interval t initial to t final into n equal parts. So in other words, let's write t final minus t initial. We're going to divide it by n, and each part, let's call it delta t. So how do we do that? Like this. Let's call t initial t1. This instant of time t2, t3, and so on. Note that t2 is t initial plus delta t, t3 is t initial plus 2 delta t, and so forth, and this is ti. Now what we are going to do for each of these intervals, each one is of a width delta t. So what we are going to do is take the first interval. The velocity at the beginning of this interval is v1 at time t1. So we are going to assume v1 remains constant for that small time interval delta t. Now we come to the instant of time t2, at which instant the velocity of the particle is given by the curve, and that's equal to v2. So for that interval of time, we are going to assume v2 remains constant. And this is how we draw our step graph. Now we know the displacement of the particle. If it followed the step graph, what would be the displacement? It would be simply v1 delta t plus v2 delta t plus v3 delta t, etc. We can write that as summation vi delta t, where vi, I going from 1 to n, are the velocities of the particle, instantaneous velocities at the times t1, t2, t3, etc., which we get from the actual velocity versus time graph. But what we have here is an expression that assumes for each time interval delta t, the velocity that we calculated at the beginning of the interval remains constant. Now, is this the total displacement for our particle from ti to tf? No. This is the displacement if the particle had followed the step graph. This is the area under the step graph. This plus this plus this plus this plus this plus this. This is not the area under the curve. You see those little parts that are left over? Out here, out here, out here, and so forth. But here is the crux of the idea. Now this area under the step graph is not a very good approximation. Why? Because for each step we assume the velocity is constant, whereas actually the velocity changed. But what if we made delta t is very small? The smaller the time interval delta t, less the velocity actually changes. So our approximation of constant velocity for each delta t becomes a better and better approximation. So let me show you with an animation what it looks like when we make delta t smaller and smaller and the number of intervals n larger and larger. So this black curve is our actual velocity versus time graph. This is t initial and this is t final. I have divided up into 10 equal intervals. So n is 10 and each of these is delta t. And let me show you what happens as I increase n and delta t shrinks. Take a look. You can see that as the number of intervals increases indefinitely, the area under the step graph approaches the area under the curve. So the area under the curve is in fact the displacement. So when the velocity versus time graph looks something like this, supposing from time t equal to 0 to this value of time, we wish to find the total displacement. It's going to be this area plus this area minus this area. That is, we calculate areas above the time axis as positive and areas below the time axis as negative. That will give us the total displacement of the particle for this time interval. Let's look at a simple example, a constant acceleration situation. Constant acceleration implies that the velocity versus time graph is a straight line. Now, the slope of the straight line is, of course, the acceleration. Let's say at time t equal to 0, the velocity is u. And at some later time t, the velocity is v. Usually, people call u the initial velocity and v the final velocity. So the total displacement during this time interval 0 to t is this area. So to find that area, what we're going to do is very simply divide it up into two parts. A rectangle whose area, this, is given by u times t. T minus 0 is the time interval, plus the area of this triangle. And what is the area of this triangle? Half base into height. So the area of the triangle is going to be half base is the time interval t times the height. The height is v minus u. V minus u. So v minus u. That is the total displacement delta x, for which usually we use the letter s. Now, since it is constant acceleration, what is the slope? The slope is the acceleration is equal to delta v by delta t, and that's going to be the change in the velocity v minus u by change in the time t. So you have v is equal to u plus at from this equation, with which we are very familiar. And let's take v minus u and substitute here. So we get s is equal to ut plus half t multiplied by v minus u. V minus u is at. At squared. So you get s equal to ut plus half at squared. You know now where that comes from. It comes from the area under the v versus t graph, and it applies only for constant acceleration. So I'm going to stop the video here. I'll see you in the next video. Bye-bye.